Okay students, this is going to be our second lecture on the Hahn Banach theorem. In the previous lecture, Hahn Banach theorem, as you already know, is about that if we have a linear subspace of a normal linear space, then any bounded linear functional defined on the subspace can be extended to the whole space without perturbing the norm. Now, in the last lecture, we went on to prove a lemma. We did not prove it actually, we started actually proving the lemma that if we extend the subspace minimally by a single vector outside it, then we can actually extend the bounded linear functional to that subspace. That is, we had our subspace y, we extended it minimally to y0, which was the subspace generated by y and a single vector outside it, x0 belonging to x minus y. Then accordingly we defined a functional f0 from y0 to r by f0 of x plus alpha times x0 is equal to f of x plus alpha times f0 at x0, and since we call this r0 a real number, and ultimately in proving the lemma we found that we just had to prove the existence. We basically had to prove that mod of f of x plus alpha times x naught is less than equal to norm of x plus alpha times x naught for all x belonging to y and alpha belonging to set of real numbers. If we can prove that, then we are done. But this was shown to be equivalent to proving that what is it? This was equivalent to showing that minus f of x by alpha minus norm of x by alpha plus x naught is less than equal to r naught, which is less than equal to minus f of x by alpha plus norm of x by alpha plus x naught. Now these two things were equivalent. So if we prove this, we have proven the theorem for the case when x is a real normal linear space, and which means the underlying field is the field of real numbers, not the complex numbers. Now then, we showed that using the linearity of f, we showed this, that for any two vectors x1, x2 belonging to y, f of x1 plus x0 is less than equal to minus f of x2 plus norm of x2 plus x0. Now this was true for x1, x2 belonging to y. Now if we choose a, b to the supremum of this set and b to be the infimum of this set, then one thing is clear, a is less than equal to b. So that means, and if we compare the two inequalities, we are supposed to prove this. If we compare these two inequalities, this one and this one here, we are supposed to prove this, but this is always true. This is true for any x1, x2 belonging to y. Now remember that x belongs to y here, and if x belongs to y, x by alpha also belongs to y, because y is a vector space. That means if we want to prove this with the help of this, it is sufficient just to show the existence of a real number that would lie between here and there, between when we get the set, while letting x1 range over all the elements of the vector space, and here letting it range over x2 range over all the elements of y. Now since this is true for all such possibilities, if we take a to be the biggest element here, right, the supremum of this set, and b to be the infimum of this set, a would be less than equal to b. So essentially it comes down to proving that there exists a real number r0 which is bigger than a and less than b. But that is obviously true, because if A is equal to B, then we take R naught equal to A or equal to B. So that would mean, if A is equal to B, just take R naught equal to A equal to B, and this is satisfied, right? And if this is satisfied, no, sorry. So this is satisfied. If we take A equal to B and this R naught, certainly there is some R naught which would satisfy this equation. Okay, and in case A is less than equal to B, A is less than B, then between two any real numbers, there exists infinitely many real numbers. So we can always find a R naught with A less than, which is bigger than A but less than B. But A is the supremum of this set and B is the infimum of this set. So that means we can always find an R naught which would satisfy this inequality. And if this inequality is satisfied by going in reverse the steps from here to here, we will get f of x plus alpha x naught is less than equal to x norm of x plus alpha x naught for all x belonging to y and alpha belonging to r. And that proves our case. That proves that f naught is indeed an extension of f which is continuous, and norm of f naught is equal to 1, which is the same as norm of f. So that proves the case of lemma. When our X is a real normed linear space. Right? Now we come to the next part of our lemma. We want to prove the lemma when X is a complex normal linear space. So now let's take this. Now let X be, case second, let X be a complex normed linear space, which means it is a linear space over the field of complex numbers. Now that means our f, which is a map from y to now c, right? That means f of x or f of y, whatever the values, they would be complex numbers, right? So if it is a complex number, it can be written as a plus iota b, where a is a real number and b is a real number, right? So what we do now suppose now we have y a complex normal linear space. But every complex normal linear space can be thought of as a real normal linear space. We just have to restrict our scalars to the set of real numbers, because R is a subset of a subfield of the complex field. So therefore, if Y is a complex normal linear space in our case, then Y must also be a Y, of course, and X, because X is the bigger space, right? Y is a subspace of this. Then Y, X or Y both are real normal linear spaces also, right? So now if F is a map from Y to C, then surely when I take its elements in the range, which would be complex numbers, that means if I take f of x, it must be of the form g of x plus iota h of x, where g of x and h of x are real numbers, where g and x are real numbers. Now if that is the case, then it is easy to show that g and h are real valued bounded linear functionals on the real normal linear space Y, because I said since Y is a complex normal linear space, we can think of it as a real normal linear space. Okay, so G and H are real valued bounded linear functionals on the real normal linear space Y, right? And since by our assumption, we are assuming that norm of f is equal to 1, then surely norm of g is less than equal to 1, because modulus of g would be less than equal to modulus of f, and when you take the supremum, that inequality would stay there. You take actually the supremum on all the vectors of norm 1. Okay. Also f is basically a complex. We are taking it to be a real valued, a real functional, but f by our definition is bounded linear functional. It's given that it is a bounded linear functional from y to c. That means if it is a linear functional from y to c, f of iota x is equal to iota times f of x, because iota is a complex number. Linearity means you can take it out. Okay, so which would imply, if I substitute it here, it would imply that, what would it imply? G of iota x plus iota h of iota x should be equal to, right, iota times g of x plus iota h of x, right? Well, I just substituted the function f. So f is given as it is here, then I just substitute the values. Now equating the real and imaginary parts on both sides, you will get that h of x is equal to minus g of iota x, which means that we can write f as, so then f, which is a bounded linear functional from y to set of complex numbers in this case, can be written as f of x is equal to g of x minus iota g of iota x. Now that makes our job easier. Now we have to deal with only one real valued bounded linear functional, right? Now if we had two, now we converted it. It's very easy actually. It was very easy to convert it into a difference of the same functional. Just a single functional is involved now. Okay, now what is g? G is a real valued, by that we mean g is a map from y to the set of real numbers, and we can consider this to be a real normed linear space, right? Now g is a real normed linear space and g is real valued bounded linear functional. So if we apply what we have done earlier for the real case, that means that by previous part of the theorem, we can extend it to the, why not? We can extend it to a bounded linear functional. So g can be extended to g naught, which is a bounded linear map from the subspace y naught to the set of real numbers, such that norm of g is equal to norm of g naught. Now, but we have to extend f, right? We can extend g because it's a real functional. We actually have to extend f, but we have to extend f as a complex valued functional from y to y naught. Okay, now what we do, we define y naught straightforward manner as g naught of x minus iota g naught of iota x. Now clearly this is a real number, this is a real number, both are linear, and this is continuous, both are continuous, so f naught would also be continuous. Now we have to verify other properties. Now clearly it is an extension. Furthermore, it is also of an extension of f automatically, right? Because g is an extension of g naught to the space y naught, it makes automatically f naught an extension of f from y to y naught. And it's linear. Now it's a straightforward exercise to show that f naught of x plus y is equal to f naught of x plus f naught of y, and of course f naught of alpha x is equal to alpha times f naught of x for all alpha belonging to R. Now simply because G is a map, is a linear functional from Y to R. Now it's defined on a real normal linear space. Now this is what we have. So it means that if I have to show that f naught is indeed linear, then I basically have to show that this equality is true for all complex numbers. Of course, real numbers are part of complex numbers, but we have to think of those complex numbers which are not purely real complex numbers. That's what we have to prove. So if we prove this part, we are going to prove the lemma, right? Good. And of course, x has to belong to y naught. Now continuing with this, now f naught at iota x would be g naught, because you remember that f naught of x is, what is it? F naught of x is g of, go to the last page, f naught of x is g naught of x minus iota times g naught of iota x. So that means f naught of iota x would be g naught of iota x minus iota times g naught of iota into iota x, right? So that would be g naught of iota x minus iota into g naught of minus x, because iota into iota is minus 1. But g naught is linear with respect to real numbers, and minus 1 can be taken out. So that would make it g naught of iota x plus iota times g naught of x, right? But I can also write it as iota times g naught of x minus iota times g naught of iota x. Very easy. So which is nothing but iota into f naught of x. Look at the definition of f naught of x. F naught of x is g naught of x minus iota times g naught of iota x. So this simple calculation shows us that f naught of iota x is equal to iota times f naught of x, right? Now we are basically done, because it is already linear with respect to the set of real numbers. And you can also take the real iota out. That means if you have an alpha, a complex number, right, you can write it as f naught of a plus iota b times x. That would be by the distributive law, yeah, whatever. So it is ax plus iota bx, right? Now that would be, since it is linear, it would be f naught of ax plus f naught of iota bx. Now that would be a times f naught of x, because a is real. Now real numbers can be taken out, right? Because we have extended it as a functional on the real normal linear space. Then you can take iota out, right? Because what we showed here. So that would be bx, but now b is a real number, and easy to show that it would be alpha times f naught of x. So we have shown that that it is linear. It is the extension of f as a complex functional, right? So the only thing that remains to be shown is that norm of f naught is 1. So only thing we need to show now is that its norm is also equal to 1. Now that is, it would be sufficient. Now if you know the definition of the norm, what is the definition of the norm? Definition of a norm would be, it would be supremum over all vectors where norm x is less than or equal to 1 mod of f naught of x. Now this is the definition, and we have to show that this quantity is actually 1. So it suffices, it is sufficient, if we show that for all x belonging to y not such that norm of x is equal to 1, then no modulus of f of x naught is less than or equal to 1, because then you take the supremum, its supremum has to be 1, right? Okay. Okay, now in case, now if f naught of x is a real number. You know that f naught of x is a complex number. It could be a purely real complex number. When I say it is a real number, I mean a purely real complex number. It doesn't have its imaginary part is 0. In that case, we know that f naught of x would be the same thing as g naught of x, right? And of course, we know that norm of g is less than equal to 1. We have already shown that, because norm of g is less than equal to 1, so norm of g naught is equal to norm of g, so therefore norm of g naught would also be less than equal to 1, because g we extended as a bounded linear real a bounded linear map defined on a real normal linear space. So in this case we don't have a problem. Now the problem would be the case that we have to sort out in case f naught x is a complex number that's not a purely real complex number. Suppose now f naught is a complex number. Let me write here non-real complex number, means which doesn't have a zero imaginary part. Now in that case, now we can write it in its polar form. F naught x is equal to r into e raised power iota theta, where r is a positive real number, right, unless it is 0. And it would imply that modulus of f naught of x in this case would be equal to r, right, which can be written as e raised power minus iota theta. We just flip it to the other side and we just take it to the other side, into f naught of x, which is, because f naught is linear, we've already shown that, it can be written as f naught of e raised power minus iota theta into x. Okay. Now remember that f naught of e raised power minus iota x is indeed a positive real number, the purely real complex number. Also, if norm of x is equal to 1, norm of e raised power minus iota theta into x, this is equivalent, not equivalent, it would imply that e raised power minus iota theta into x is also equal to 1, because modulus of e raised power iota theta, whatever it is always equal to 1, right? So that means that firstly what we've got f naught e raised power minus iota theta x is a real number, right? It's r, right? And since it is a real number, then the previous what we have done, it means that modulus of f naught e raised power minus iota theta into x is less than equal to 1, right? Which would imply, now this is true for all x belonging to y naught with norm of x less than equal to 1. Rather equal to 1, but that's the same thing. Which implies norm of f naught is equal to 1. So that finishes the proof of the lemma. And I don't know whether we should continue. How many minutes? Now we come to the proof of the theorem now. Using this lemma, we can now prove the theorem. Okay, I should stop here because it's getting bigger. It can't be then uploaded.